Next preparation is from anhydride. With anhydride, just you add water, you will be getting you just add water with the anhydride. For example, C6H5, C double bond O, C double bond O, CH. Just add water, you will be getting carboxylic acid. That is C6 2 carboxylic acid, C6H5, COOH, and CH3, COOH. Two carboxylic acids you will be getting by adding water to anhydride. Next is from alcohol. From alcohol. Oxidation with the strong oxidizing agents like alkaline KMnO4, acidic KMnO4, alkaline K2Cl2O7, acidic K2Cl2O7. So CH3, CH2OH, alkaline K, strong oxidizing will give you CH3OH. You'll be getting carboxylic acid. From hydrocarbons, aromatic hydrocarbons. From aromatic hydrocarbon, whatever may be the side chain length with carbon, all will be getting converted into, for example, CH2, CH2. Whatever may be the length of the hydrocarbon, everything will be getting oxidized to what carboxylic acid. Carbon should be there. The side chain, carbon should be there. Next method of preparation is from Grignard reagent. With Grignard reagent, that is MgBr, aromatic or aliphatic. C6H5MgBr, you introduce carbon dioxide. You introduce carbon dioxide into this. So you will be getting, see that carbon dioxide is incorporated in this thing. Acidification or MgBr. Acidification will give carboxylic acid. So to convert an aromatic, we are connected to this benzene ring. You can first convert into a Grignard reagent by putting Mg. By putting Mg. By putting Mg, you can make it Grignard reagents, and correspondingly you can make the carboxylic acid. Otherwise, we know that CBr bond is not local due to the double character. Due to the double bond character. So those are the preparations of carboxylic acid. Next, let's move to the physical properties and chemical properties. Carboxylic acid. Carboxylic acid exists as a dimer. That is the main point here. Carboxylic acid exists. COOH. Another CH3. COOH. Exists as a dimer. So molecular mass, if you calculate, you will be getting double due to this dimerization. Physical, so the boiling points and melting points, corresponding boiling point and melting points will be higher because of this dimerization. With chemical properties, are they soluble in water? Carboxylic acids are soluble in water. For the smaller ones, that is carboxylic acid having up to 4 carbon atoms are miscible with hot water due to hydrogen bond formation. But if the hydrocarbon part increases, that means oily part increases, the solubility decreases. When you consider the boiling points of carboxylic acids are higher than that of phenols, alcohols. Alcohols, we know hydrogen bonding, among them hydrogen bonding is there, but here not only hydrogen bonding, they exist as dimers, so it becomes heavy. So carboxylic acids are having, this is extensive hydrogen bonding is there, dimerization is there, so their boiling points are very high, than these alcohols. Chemical reaction, first one, that is COOH. First, we are going to learn acidic character. Acidic character, phenol is acidic, but carboxylic acids are much more acidic than phenol. Phenol could react with NaOH, but with NaHCO3, phenol would not react with NaHCO3. Carboxylic acid can even react with NaHCO3. Means weak bases also carboxylic acid can react. So by this test you can distinguish a carboxylic acid from phenol. Carboxylic acid will react with NaHCO3, that is NaHCO3, you will be getting corresponding salt, that is CH3, and H2O and CO2. There will be liberation of carbon dioxide. But phenol, such liberation of carbon dioxide, phenol will not react with NaCO3, so no liberation of carbon dioxide. Carboxylic acid can react with metallic sodium and will liberate hydrogen gas. Carboxyl can react with NaOH, salt and water. It will react with NaCO3, liberation of carbon dioxide. So with Na and NaOH, it was also given, but with NaCO3, only carboxylic acid will be given. So this is a distinction test between carboxylic acid and phenol. Now, when you put carboxylic acid in water, that is COOH plus H2O. It's a weak acid, so you can expect an equilibrium between dissociated and undissociated. So here you will be getting H3O plus, it will be H plus, so H3O plus and CH3COO minus. So here Ka value, equilibrium constant for acid, instead of Kc you can write Ka, and that is equal to into this is actress into CH3COO minus and CH3COOH undissociated. These are remaining conservation. Ka value is not a good value to see, so we convert the Ka into pKa by taking minus Ka last equivalent. So pKa value is a small number, that is minus log Ka. pKa value, as pKa value increases, acidic character decreases. I am giving you some pKa values of different acids. That is HCl, pKa minus 7, CF3COOH 0.23. Moderate acid, normally like CF3COOH, moderate acids, that is 5 to 6. Phenol 10. Ethanol. See, as pKa value increases, acidic character decreases. So in this way you can see the range of acidic character on basis of pKa. pKa is a small number, but Ka value is complicated number, like 1.77 into 10 to the power minus 5, like that. But pKa will be getting it small numbers. Now we said carboxylic acid is more acidic than phenol. carboxylic acid. In carboxylic acid, RCOOH. After the liberation of H plus, the anion found is called carboxylate ion. We said carboxylate ion is more stable than carboxylic acid, so carboxylic acid easily gets converted to carboxylate ion, which shows the acidic character. Similarly, we learned in the case of phenol also. Phenoxide ion is more stable than phenol, so phenol easily changes into phenoxide ion. That shows the acidic character of phenol. So I am writing phenoxide ion. Phenoxide ion. Carboxylic acid, carboxylic ion has got 4 resonance structures, but phenoxide ion has got 5 resonance structures. You can show this 5 resonance structures. I have already shown that. Here, carboxylate ion has got 2 resonance structures, and we write that resonance structure is R, C, double bond O, single bond minus. It has got 2 resonance structures, that has got 5 resonance structures. Here, carboxylate ions, of course, it has got 2 resonance structures, but carboxylate ion means its contribution is 50-50. Equivalent contribution, and negative charge is on the more electronegative oxygen, but here negative charge is on less electronegative oxygen. Negative charge should be on more electronegative oxygen. This is stable nature, not on electropositive carbon. Negative charge is suitable or more stable on electronegative atom. Here, these are having equivalent resonance structures. They are having non-equivalent resonance structures. They are having equivalent resonance structures. They are having non-equivalent resonance structures. This equivalent resonance structures means more stability for this carboxylate ion. So carboxylate ion is more stable than carboxylic acid as compared to the relation between phenol and phenoxide ion. Iron is stable than phenol, but phenoxide ion is not a good ion as compared to this carboxylate. So, what are the reasons? These are having equivalent resonance structures, and number 2, negative charge is on electronegative oxygen, while negative charge is on less electronegative carbon. So carboxylate ion is more stable than phenoxide ion. So carboxylic acid is now coming to the acidic character. CH3, COOH. Due to this resonating nature, there is always electron density on that carbon. It's not a pure carbonyl compound. There is problem. It's not a pure carbonyl compound. Due to this resonance, presence of electrons are there. Suppose if it is attached to a benzene ring. Due to the presence of electron density here, this will be showing what minus R. Or more clearly, we can say sp2 hydrous carbon atom. sp2 hybridized carbon atom is electronegative. So that electronegative sp2 hybridized carbon will be pulling that electron density from there. So attachment of C6H5 will increase the acidic character. Generally, we can say electron withdrawing groups will increase the acidic character. electron donating group will be decreased in the acid character. On carbon, there is the presence of electron density. So C6H5 will be taking the electron density from that carbon, which is having electron density, electron presence, not much, but there is electron density due to the resonance. So an attachment of C6H5 will increase the acidic character due to that sp2 hybridized. Here, that C6H5 will not show plus R effects. It will not show plus R effect. Next, cleavage of C bond OH. R C double bond OH. Cleavage of this. This shows what the reactions of Lucas reagents. PCl3, PCl5, SOCl2 and SOCl2. That means this OH can be replaced. OH can be replaced and the corresponding Cl can come over here. Corresponding say PCl3, PCl5, SOCl2. What we have seen in the case of alcohol, the same reactions are occurring. Another typical reaction of carboxylic acid is on heating. On heating, they lose water molecule and an anhydride will be formed. Adding water to anhydride, you can get carboxylic acid. Removal of water from here, you can get what? Anhydride. Oh. Carboxylic acid can undergo esterification also. Carboxylic acid can undergo esterification reaction. Esterification, that means an acid and an alcohol. An acid and an alcohol. That is RCO. There are 5 steps for the mechanism of this esterification. And this first one is protonation. Number 2, adding alcohol. Number 3, proton transfer. Number 4, removal of water. And last, dechlorination. First one is protonation. We are protonating this to increase the electrophilicity of carbon. We know that the carbon is not much positive. So to increase the positive character of the carbon, we are doing protonation. So H plus. So R using this pair of electrons R C O H. This is OH. Now you see this pair of electrons will be going to cancel that positive charge means electrophilicity of the positive nature of carbon will be increased. Next is adding alcohol R2H. So this pair of electrons you can attack on this carbon. So R C OH, that is OH, then here. This OH and this OH I am putting down, and this O R H. O R H I have put like this now. This is having positive charge. Next is what? Proton transfer. This pair of electron will be taken here, so H will be going here. This has got pairs of electron. So next is proton transfer. So R C OH here OH H plus and OR. Next is removal of water minus H2O. This pair of electron will be taken to cancel the positive charge, that water will be removed. So here R C OH, then what is plus, that is OR. Next, deprotonation means this H, deprotonation, H will go here, H plus will go, and the pair of electron will be taken to cancel that positive charge. So next is what R, C, the double bond O now retains, that is O. I'll be putting a star on this O18. Here I have put O18 to show that this is coming from, that oxygen is coming from alcohol. So this is the mechanism. What's the mechanism? Yes, so first is protonation, adding alcohol, proton transfer. This is the proton transfer, and next is removal of water, and then deprotonation, that is minus H plus, that is deprotonation. Next reaction of carboxylic acid is a reaction with ammonium. Reaction with ammonium. NH10. Carboxylic acid CH3 COOH plus ammonia. Ammonia is a base. Carboxylic acid is an acid. So what is formed? Here is C. CO. ONH4 plus and minus. Salt is formed. Minus and plus. Salt is formed. Now, from here, one molecule of water will be going, and you are getting that is H2O. H2O, that is CH3. CONH. Means an amide is formed by using one molecule of water minus H2O, that is amide will be formed. Consider organic, that is benzoic acid. Benzoic acid. Okay, one more C with the two carboxylic group. Halic acid. This is called PHEH, halic acid. Halic acid can react with ammonium. So both the substances have, that is CO minus N4 plus, and here CO minus N4 plus. Means finally removal of water from there and removal of water from here. You get your NH2. NH2 here. H2O will be going. So here again NH2. From here, you will be getting a compound. This is called the thalamide. Thalamide. Okay. Then COOH. This will be obtained. So this is thalamide. PHEH. Thalamide. This is thalamide. So this is a reaction with ammonia. Next type of reaction. So first we learned the acidic character of carboxylic acid. Then we learned the breakage of OH bond, breakage of OH bond, esterification, breakage of OH bond. Then we learned the reaction with ammonia, and next reaction is reaction with ammonia is again an example for cleavage of OH bond. Cleavage of OH bond, see that OH bond is moved and NH2 is coming over there. Next type of reaction, that is, first is acidic character, next is cleavage of that OH. Now third is the reaction of COOH together. CH3. Reaction of this together. COOH. Reaction of that together. That is, the first one is a reaction with lithium aluminum hydride. Lithium aluminum hydride. What you are going to get? Corresponding alcohol, that is CH2. Benzyl alcohol. Same number of carbon atoms, you are getting an alcohol. Corresponding alcohol, you will be getting. Next is from the sodium salt of this. From the sodium salt of this, that is sodium benzoate. Sodium benzoate on heating with soda lime. Last time we learned this reaction with the soda lime. Soda lime is a mixture of calcium oxide and sodium hydroxide. Calcium oxide and sodium hydroxide. So one Na2CO3 will be going, one Na2CO3 will be going. You wrote like this last time. That is Na2CO3 will be going. What is soda lime? Soda lime is a mixture of sodium hydroxide and calcium oxide. So you are getting a hydrocarbon. You are getting benzene. You will be getting a hydrocarbon smell, petrol-like smell. You will be getting. So benzene plus Na2CO. The last reaction of carboxylic acid is substitution. So soda lime. Soda lime. Na2CO3. This H will be here. H will be. Next, substitution and hydrocarbon. R6, that is the last type of reaction, that is okay. Substitution and hydrocarbon, that is RCH2OH, RCH2COOH. Substitution at this on alpha carbon, that is red phosphorus and fluorine. Red phosphorus and fluorine. One hydrogen will be replaced and you will be getting a halogen. This reaction is called HBZ reaction. That is RCHCl That is alpha halocarboxylic acid. Alpha halocarboxylic acid. This reaction is known as HBZ reaction. This reaction is known as Hell-Volhad-Selinsky reaction. Hell-Volhad-Selinsky reaction. So if you want to put a halogen in this carboxylic acid, you can put it at alpha carbon, chlorine or bromine, whatever it is will be attached on this alpha carbon. For electrophilic substitution, that we will do in the next class. That is the last reaction, electrophilic substitution. Thank you.